Continuing on, thanks everyone for sticking around. We're now starting our last session of the afternoon. It's going to be Beyond Smart Cards, Open Source Authenticator Innovation. And we have two presenters from SoloKey. We have Nick Stalder, who's the CTO and co-founder, as well as Conor Patrick, who is also a co-founder of SoloKey. Unfortunately, they couldn't actually be with us in person, so they'll be live, but doing it remotely. So I'm handing it over to our tech guys, who can now hand it over to them. Welcome and thank you, guys.
Hello. And it'll just be me, Conor. Fortunately, Nicolas could not make it today, but that's okay. I know this presentation both very well. So thanks for the introduction, and I guess I'll get started. So this is Beyond the Smart Card, Open Source Authenticator Innovation. I'm Conor, and I'm from a small company called SoloKeys, where we make open source physical authenticators that support FIDO2, PIV, and other applications like one-time code generation, time-based one-time code generation. We got started back in 2018 with a crowdfunding campaign, just a 4-person company. Myself, Nicolas, another person, Manuel, and my brother, Hayden, started this company. I originally started working on open source authenticators back when I was in undergrad. I made a little project called U2F0, made it all on my own, and I started kind of distributing them in the US. That's where Nicolas saw the project. He really liked the idea of making open source authenticators. I guess back then it was just U2F. FIDO organization was pretty new, or there was no FIDO2 back then. It was only U2F. Anyways, Nicolas saw the project and he really liked the idea and he thought he wanted to help. And so he messaged me. He's like, hey, can I start distributing U2F0s in Europe? He's based in Switzerland. I'm like, oh yeah, sure. So our little company was 2 people. And then our third person, Manuela, he worked at security at Pinterest, and he was working on a personal project making wearable authenticators and was looking to kind of expand. And so he saw us. We're kind of the only open source authenticator project at the time, and so joined up with us. And then my brother was finishing up his MBA at the time and wanted to join it. And so around 2018, we started this project with our first Kickstarter campaign, and I've been, since then, I've released about 5 different open source authenticators. However, I'm not here to try to sell you on buying like our authenticators or SoloKeys or anything like that. We just really want to talk about one point, and that's the future of hardware authentication needs open source. We've run into like a number of problems working, or at least trying to innovate on making security authentication on hardware. I guess one of the glaring issues is so much security with hardware is based on NDAs, or non-disclosure agreements, which kind of makes sense because a lot of the if there's an exploit or a security bug in a secure microcontroller or something like that, it'd be very expensive to fix because you can't just patch it. You have to make a new chip. And then another problem is the certifications, like EAL6 plus certifications, FIPS. Once hardware goes through these very expensive certifications, they essentially become very, very use-specific bricks. So it's very hard to like change them without a lot of expense or having to redo your certification. But the existing use for, I guess, secure hardware, secure microcontrollers, like on your payment cards like Visa or MasterCard, or the chip on Apple Pay or Android Pay, what have you, like it works very well. There's no one that is concerned with their chip being duplicated or hacked or anything like that. And it's fast and it's cheap. But the concern comes like when you want to kind of do something else and innovate for a new use case, or in our case specifically authentication. other FIDO authenticators on the market, like ATN, Yubico, or other like cryptocurrency wallets, other modern secure hardware we see, it's pretty often that they use this technology. And for all the products that typically do use this secure hardware, we don't really see very much open source or for the firmware that's using the secure microcontrollers. And this makes sense because in order to get access to these secure microcontrollers, you need to have a very high level of assurance to be able to even sign these NDAs. It's sort of like getting a security clearance with the government or something. These secure microcontrollers are held very tightly and protected very closely. So now if we take a step back and just think about the impact of open source in all other projects, like any database software, SQL, Postgres, LevelDB, it's all has an open source core. It's pretty unheard of to use database today in new applications with a proprietary database. And yet a secure element or a secure microcontroller, you can kind of think it's essentially just a database, but for like cryptographic secrets for one person. LLVM, the kind of open source compiler extensions and tools that powers most modern programming languages, it's open source. We wouldn't really see like Rust, Swift, or Kotlin, or as they are today, without LLVM. Golang, I don't believe it uses LLVM, but it's completely open source. And really any modern programming language today is open source. You're not ever going to see a proprietary programming language or a copyrighted programming language get very far, get much popularity. It just wouldn't be able to innovate quickly enough. And using the choice of a programming language today is incredibly important to innovate. Just to give an example with LevelDB, which is a very popular key value store database made by Google. Its original and most mature implementation is in C++, has the most commits, the most auditing. It's the highest performant implementation of LevelDB. But if you look at blockchains, at cryptocurrency, one of LevelDB is a kind of a core primitive behind the Tendermint Byzantine fault tolerant consensus algorithm. That if you were to look at the current valuation of these projects, it's over $130 billion, and none of them are using the C++ implementation of LevelDB. They're using the Golang implementation. Like, it's a little bit slower, but if you have to protect a lot of assets, it doesn't matter. You don't want to use an implementation in a language that isn't memory safe. It's just, especially with like something that's public facing. So with the secure chips, it's a little bit different. You're not, with programming microcontrollers in general to make like an authenticator, you can have your choice of programming language that you want to use. You're going to have to put in a lot more work to be able to support the drivers on the microcontroller, maybe like the AES engine or the USB driver, what have you. And with whatever microcontroller, even secure or not, all of the libraries and supporting examples, documentation is all going to be based on using C. They're not going to be able to use Rust or Golang. The industry just kind of hasn't really caught up yet. And secure microcontrollers are even more behind, I would argue. To be able, the easiest way to be able to use them is through Java Card, where they don't give you bare metal access to the microcontroller. They don't give you the datasheet or anything. They just give you the chip as a black box, and it has Java Card programmed, or Java Card runtime programmed on it. And then you as a developer just put Java Card applets on it. So you almost don't care which microcontroller it is. All these details are abstracted to you. And this kind of protects the manufacturer from a little bit more from leaking information about the bare metal of the chip, and then developer can develop on the microcontroller without having to sign as high of an assurance NDA. Unfortunately, Java card is like a huge pain to work with. It was kind of designed decades ago. I don't think it would really be feasible, practical to implement FIDO2, for example, in Java card. Basically, the only way is if the manufacturer implemented FIDO2 on their own, and then they just kind of expose it to you as a method in Java card. But anyways, so for us, SoloKeys, when we want to make an authenticator, and we're kind of looking at, okay, a secure chip with a certification would be nice, but it's sort of like when you make an account, you set your password and everything, and then it asks you for security questions, like what's the name of your first pet, what's your dream job, and you essentially have to set 2 or 3 more passwords. Like, sure, it maybe could make your account more secure, but this is 2021. We don't do this anymore. We don't want to deal with that crap. So back in 2019, this is kind of like when we were like making this decision. Nicolas, we just finished shipping our first generation of Authenticator products. They're all written in C. We hadn't innovated quite that much yet. It was just open source. And Nicolas, he asked me like, oh, let's start over. Let's just rewrite everything in Rust. It'll be a lot safer and we'll be able to do a lot more. And I'm like, well, okay, sure. Can't be that bad. We picked a new microcontroller. It's not one of the quote unquote secure microcontrollers, but it's something that anyone can buy and program for bare metal on the open market. It has a number of really nice features that we can get pretty far with. USB high speeds, support secure boot, hardware encryption, hardware accelerated asymmetric encryption, physical encodable function, write-only keys, all these features. And so even though it's maybe not the pure state-of-the-art secure microcontroller, we can still get pretty far with making a pretty good authenticator with this. Unfortunately, there aren't any manufacturer SDKs for microcontrollers that are in Rust. The only ones that I know of are made by people and are published on GitHub, and usually they're a lot better quality than the manufacturer provided libraries. For us, there wasn't anything yet, and so we had to write everything in Rust, which is initially quite a challenge, especially writing the USB device driver. That's something Nicolas did, and it took him, say, many weeks and a lot of hard debugging. I similarly wrote up the NFC communication stack, which is pretty challenging to do from scratch and when it's operating and passively without any power. But anyway, we got all these drivers written and we got this abstraction layer finished. And once we did that, the fog is cleared and it's immediately worth the effort from a productivity perspective. We can start immediately benefiting from the Rust ecosystem. So we could essentially have our choice of which real-time operating system we wanted to use. We used probably one of the best, RTIC, previously known as RTFM. We could also use the really awesome Rust crypto libraries. So any modern cryptographic primitive is probably already a nice constant time and well implemented implementation in the Rust crypto organization. And this is typically a huge challenge in embedded systems. It's not like you can just import OpenSSL or what have you, because these libraries are designed to kind of run on a rich operating system, not on a bare metal or real-time operating system microcontroller. So really, it's really tough to be able to find cryptographic implementations that don't have system calls basically and are designed to run in lightweight scenarios. Fortunately, most everything in Rust crypto is designed to be like that. And then many more libraries that essentially, I mean, all of these, it's as easy as, cargo install, ... whatever library you want, and then you can immediately start using it. No worrying about intricate build systems and build problems. A lot of this is very seamless. Where the strongest benefit isn't, at least for us, isn't so much the productivity, but the strong security benefit that you get from Rust or implementing something in another modern programming language. So we essentially have built a very rich, arguably complex software core with a lot of cryptographic APIs, serialization, deserialization that made FIDO2 very trivial to implement on, and we could feel very safe with because it's a memory safe language and so much more functionality that you would kind of have to run into at runtime, knowingly or not. This functionality can be guaranteed or checked at compile time. And this is really like a modern innovation that we more or less get for free by using Rust or maybe some other language. I think Rust is really the best at this. And it's especially nice for an open source security project because there's always a trade-off with open source security. On one hand, if your project is open source, it gets more eyes on it, you get more feedback, you get more trust from the community. But on the downside, an attacker can see your code and may be able to find an exploit faster. Now, I would say that this is certainly true if you write in a language that's not memory safe, and it's much less of a concern if you write in a memory safe language, especially for like the kind of project that we're working on where it's a little authenticator with one interface to communicate with. So when we ship this, or business at this point, like we did all this work on software, and then all we did is just kind of download the software core on our chosen microcontroller, and like, all right, now it's a FIDO2 authenticator, and then this is what we shipped. The reason why it's so easy is because we spent a lot of work on making a good abstraction interface for getting the cryptographic APIs that a FIDO2 authenticator would need. And yeah, we launched with a crowdfunding campaign and we shipped everything, or we're in the process of shipping everything. We're pretty late with the supply chain issues, but we raised around 500 to 600K. And so thanks a lot for those of you that supported us. Now, I only have a few minutes left, so I'm gonna skip ahead with a couple ideas that we think are pretty interesting to us. One is this idea called trust, where essentially, rather than downloading the software core to an authenticator and using it as an external authenticator, could download it to a trusted execution environment and turn that trusted execution environment into a modern authenticator. So that could be like a secure enclave, Intel SGX, ARM Trust Zone, AMD SCV, what have you. So it's similar to using like a TPM as a platform authenticator, but rather than having to wait on the latest generation of TPM, you can just download the latest version of Trust or the latest version of XYZ open source project and get the latest authenticator you need installed on your T, which I think would be really exciting. Another really exciting area is threshold cryptography. So this is the idea where you have a cryptographic private key and you split this into multiple shares. And then the holders of those shares need to perform multi-party computation, communication with each other to compute some cryptographic output like a signature. So in FIDO, this may sound at first impractical, but there could be a relying party that needs to collect partial signatures from multiple authenticator holders. And so in order to complete a signature, you need to have multiple people plug their authenticator in and advance the multi-party computation another step, similar to like multi-signature, but cryptographically enforced. It may not make sense to have all employees do this, but the employees with the very high privileged credentials, I think this is very much the next step. And we see this a lot in the cryptocurrency space, and we've actually seen quite a lot of recent innovations in threshold cryptography that really empowers these kinds of techniques. So yeah, just kind of food for thought. The first authentication mechanism is the password, which is a single symmetric secret. And now we're using kind of multiple authenticators that use asymmetric secrets. And we think kind of like the next step is kind of splitting those authenticators into separate shares or downloading those authenticators to trusted execution environments. And you don't need to buy an external authenticator. And if you are running a state-of-the-art authentication system and you want to be able to support the latest and greatest special cryptography or trusted execution environments, you will be behind if you're using yesterday's secure microcontrollers or Java card or the old standard interfaces like PKCS11. So when it comes to moving fast and innovating, open source is critical. And I hope that we have convinced you of that or moved you further down the spectrum towards open source. For other projects that are kind of related to what I've talked about, check out the USB Armory, kind of another external trusted execution environment / authenticator. Occlusions Armistice tooling based on the USB Armory. eNarcs, I hope I'm pronouncing that right, but just kind of like a Rust-based framework for installing applications in AMD SCV, which is like a server-side trusted execution environment. Think about a framework for installing applications that then root a server on a root could not access anymore. Check out Monogon's Metropolis project. They're essentially just building like a very small ELF file that boots straightly from UEFI. So rather than running like Linux or something, you just boot straightly into a firmware of sorts. You just convert like a server into a very purpose-specific authenticator of sorts. Great. That's it for my talk, but I didn't go over too much. Any questions?
Thank you, Conor. There's no questions online. Do we have any questions here from the audience? Yes, actually, I gotta run with the microphone.
Yeah, thank you for your presentation. My question is particularly about threshold cryptography. So multi-party computation is usually, it's very commonly people talk about like the general purpose computation, but you talked about some interesting routines like key generation and signature. So can you give one example of, are you talking about digital signature when you talk about threshold cryptography? And if you are, can you give one example how the shares, I'm assuming that you're gonna work with the threshold, so, which is an interesting concept. So how digital signature is actually performed in the real world using threshold cryptography. So that's very interesting.
Yeah, so there's a number of frameworks that define how this is used, and it depends a bit on which elliptic curve that you're using for signing. And yes, I am talking mostly just for signatures. There's like the Frost framework and the GG20 framework. I should have listed these, but essentially it defines the algebra and the communication that's needed, where the private key is split into shares. And if we were using this on authenticators, I guess it doesn't matter if it's on an authenticator or not. But there's a number of steps for that the participating parties can participate in. One, to like generate a key that is represented in these various shares that you can then use N of T or 2 of 3 of those shares to then produce a valid signature from those participants. So I hope that answers your question.
Great, thanks. Do we have anyone else? No? Well, I want to thank you again, Conor, for giving this presentation. We appreciate it.